avant toute chose, bonjour à tous et puis bienvenue pour cet après-midi de présentation qui rentre dans le cadre des Zooms de la SFGP et organisé par le groupe thématique Ingénierie avancée des procédés. Alors aujourd'hui, le thème général, c'est l'intelligence artificielle, outil incontournable pour le génie des procédés, avec un focus particulier sur les méthodes d'apprentissage. Alors, le programme que nous allons suivre donc, est le suivant. Donc, après un mot d'introduction de quelques minutes réalisé par Jean-François, nous aurons deux présentations réalisées par deux chercheurs italiens. Donc aujourd'hui, c'est Forza Italia. Donc une première présentation réalisée par Veronica Piccialli de l'Università de Rome, qui nous fera une présentation sur un overview sur les méthodes de machine learning possibles. Et s'en suivra une présentation réalisée par Bernardetta Addis, qui nous fera une présentation sur une étude de cas qui donnera une combinaison entre les méthodes d'optimisation et des méthodes de machine learning appliquées dans le domaine de séparation de mélange gaz à travers des modules membraneux. Alors, pour ces deux présentations, nous vous recommandons chaudement de poser vos questions via l'option Puis et R proposée par Zoom. Et alors, les deux présentations seront réalisées en anglais et dans la mesure du possible, vos questions devront être en anglais et dans le cas de difficultés, n'hésitez pas à écrire vos questions en français et nous traduirons si besoin. Alors, juste avant de laisser le mot à Jean-François pour son mot d'introduction sur la SFGP, nous vous rappelons simplement que ces Zooms de la SFGP organisés par le groupe thématique Ingénierie avancée des procédés s'inscrit dans une thématique, une organisation générale sur le lien qui existe entre l'intelligence artificielle et le génie des procédés. Ça fait suite à une première session réalisée le 28 janvier 2021, dont l'intitulé était « Intelligence artificielle au service du génie des procédés », d'une approche Big Data ou Machine Learning, Deep Learning à l'usine 4.0. Aujourd'hui, la session du 6 juillet 2021 a un focus sur les méthodes d'apprentissage. Deux sessions sont déjà prévues. La session suivante sera réalisée le 16 septembre 2021 avec un focus particulier sur l'utilisation des modèles d'apprentissage dans les procédés. Et enfin, la dernière session prévue pour cette année 2021 laissera la part belle à des ateliers de démonstration. Le focus sera la mise en pratique sur les méthodes d'apprentissage avec différents ateliers de démonstration. Donc voilà, je vais laisser donc la main à Jean-François qui va nous faire un mot d'introduction de la SFGP. Jean-François.
Oui, merci Roda. Bon, rassurez-vous, je vais être court.
Je vais arrêter le partage.
Au nom de la SFGP, moi, je suis très heureux de voir cette dynamique qui continue sur l'organisation des Zooms. Donc, avec un GTIAP qui est vraiment très pushy là-dessus. Donc, merci à vous. Je sais bien que l'année a été difficile, bon, un peu plus qu'une année, mais on a pu maintenir une animation scientifique au travers de ces Zooms. Donc, un grand merci à Martine qui a vraiment impulsé ça depuis plusieurs mois. Donc, c'est vraiment un beau succès. Alors, pour l'année qui vient, on va poursuivre les Zooms. On a tous bon espoir et une certaine hâte que cette situation actuelle de confinement et de difficultés pour travailler sur site disparaisse. Cependant, je pense qu'on va garder cette activité de Zoom qui nous permet de rassembler un peu notre communauté en grand nombre assez facilement. Et on la complétera par ce qu'on faisait précédemment, à savoir des réunions de GT en présentiel. Alors, c'est quelque chose qui est très important parce que finalement, les GT, c'est le lieu de rencontre privilégié entre notre communauté académique et la communauté industrielle. C'est là où on peut partager sur des topics, on peut mieux se connaître, voire initier des futures collaborations. Donc, le présentiel est quand même quelque chose d'important. Donc, la première grande réunion qu'on fera en présentiel cette année, ça va être une Catala Lotor au mois de novembre. Tom, Martine me corrigera. Disons au deuxième semestre sur l'ingénierie.
Les dates, c'est le 16 et le 17 novembre à Paris.
Novembre, c'est bien ce qui me semblait. On fera ça à Paris en présentiel sur l'ingénierie circulaire. Et en 2022, on aura le congrès bisannuel qui se tiendra à Toulouse et qui est co-organisé avec l'équipe de Montpellier. En fait, c'est le congrès qui sera porté par la section Grand Sud-Ouest de la SFGP. Donc, merci à toutes et à tous d'être venus nombreux. Je vois qu'il y a 94 participants. Ça montre l'intérêt que vous portez à l'activité du GT, à cette forme de Zoom. Et j'espère que vous trouverez satisfaction dans les présentations et que la discussion sera riche. Donc, un grand merci à Roda et à Ludovic pour l'organisation et je vous rends la parole. Roda, à toi. Merci.
Merci Jean-François. Donc, it's now I'm going to pass it's time to Veronica to present her speech. Donc, it's up to you.
Okay, I'll share the screen a second. Okay, so good afternoon to everybody. Sorry for not speaking French, so my talk will be in English. And what I'm going to give you today is a rough introduction, a very high-level introduction to machine learning in general and what kind of problems we want to solve in machine learning. And then I will go through some methods for supervised classification problems in machine learning mainly, because the idea is that then Berna will give you some application of a regression problem. So what is the problem we want to handle? What is what we want to do? Well, what we would like to do is predictive data analytics. And what is predictive data analytics is the heart of building and using models that make predictions on the basis of patterns extracted from historical data. And if you think about it for a second, we have applications of predictive data analytics everywhere around us. If you think about it, search engines learn how to give us the best results on the web. We have anti-spam software that learns how to filter our email messages. And our credit card transactions are protected by some software that has to learn to detect fraud. And digital cameras learn to detect faces. And smart personal assistance applications on smartphone learn to recognize our voice commands. So we are surrounded by many, many of these applications. I'm going to look in details to some of these to show you the kind of main problem we want to handle with machine learning. And the first one is the email spam filtering. So we have, in general, when we are building an anti-spam filter, then we have a number of emails that have been labeled by hand. So we have a human subject that takes a set of emails and says, okay, this one is a good one, this one is spam, this one is a good one, and so on. And for each one of these emails, we also have recorded the relative frequencies of some common keywords. And the aim in this context is to build a predictor that is able, given a new email, not the one we have already seen and used to learn, to decide whether that email is a spam or not. So what I want to do is to be able, when I see a new email, to decide whether that is a spam email or not. And it is, in this case, this belongs to the general class of binary classification, supervised classification problem. I'm saying binary because we only have two classes, spam or not spam. I'm saying classification because we have to basically decide decide belonging to a class. And then I'm saying supervised because you have a training set where you already have the labels. So this is the first examples of predictive data analytics problems. So I want to solve a binary classification problem. Another example here, we have in this case, our data set is made by 97 measurements for clinical measurements for each, so on each row I have a subject, and then I have 97 columns. And on each column, I have a clinical measure. And what I want, my last column now, before it was the label spam or not spam, now is the amount of a specific of PSA, which is a prostate-specific antigen, that is an enzyme that is produced by the prostate and that increases only if there is something wrong. And in this case, what I would like to build on the basis of this data set is a predictor that, given these 97 measurements, predicts the logarithm of the PSA. And the logarithm, I'm saying the logarithm and not the exact number, because I don't care about the exact number, but I want the order of magnitude of my enzyme, okay? And so in this case, since what I want to predict is some continuous value, then it is a regression problem. Okay, so this is an example of regression problem. Another famous problem that gives rise to a famous data set, which is called NIST, is where the data come from some handwritten zip codes in the US letter envelopes. And each image represents one digit of the 5 in the zip code. And this time, each image is being cropped and resized so that more or less they have the same size and orientation. And for each pixel, you have a number from 0 to 255 that tells you what is the intensity of that pixel. And in this case, what you want to build is a predictor that, given the image, will give you which number between 0 and 9 is represented in that image, so that you can easily send the envelopes in the right count, right state in the US. And in this case, so it's again a classification problem, because you have to recognize among a finite number of classes. In this case, you have 10 classes, the numbers from 0 to 9. And so in this case, it is a multi-class classification problem, okay? So in general, when you're doing predictive data analytics, we have mainly two kind of problems we want to solve. The first one is a classification one. In this case, the predicted output is categorical, in the sense that you can only assume a finite number of values. And if I'm doing supervised classification, I know already in advance what is the number of classes I want to classify into. So what I have to decide is, among a given number of classes, what is the right class for my instance? Or it can be unsupervised. And in this case, I want to find some similarity classes, some clusters. And then I also have, in this case, to decide how many classes I want to find. And then I have regression problems. And in this case, what you want to predict is a specific numerical value. So it's not class membership, but just some specific numeric value, as we had in the PSA example. So more in detail, if I'm doing supervised classification, each row of my data set represents a pattern, and the pattern is an object. It is described by finite sets of numeric attributes that are also called features. And when I'm doing supervised classification, there are some representative patterns that are given of some classes, and these patterns are known a priori. And the idea is I want to build a mathematical model that, given a generic pattern belonging to the space, to the feature space, defines the corresponding class of affiliation. So as in these examples, I know that I have two classes, squares and circles, and have examples in my training set of both classes. On the other hand, if I'm doing unsupervised classification, again, I have a pattern that is an object described by finite set of numeric features, but I don't know a priori some representative patterns of classes. So what I would like to do is to determine the number of classes of similarity and build a mathematical model that, given a generic pattern belonging to my input space, defines the corresponding class. So this time I only have circles, and depending on how many classes I'm choosing, whether 2 or 3, I'm getting different outputs, you see. So in this case, I don't know what is the right number of classes, and I don't know exactly in advance, so I don't have labels in advance, which is why this goes under the name of unsupervised classification. So what is machine learning? Well, machine learning refers to the automatic detection of meaningful patterns in data. And since many huge data sets have been available in the last years, it has become increasingly important. And in this context, due to the complexity of the patterns we want to find, we cannot provide a program like the way we were used to, so like a sequence of instructions that the computer should execute in order to get the task done. So we need machine learning whenever we have to provide my program with the ability to learn, and we are not able to give just an instruction flow that performs that task. And so the question is, what is learning? Okay, so what does learning mean? And we take some examples from the animals. So think about rats, okay? When rats encounter some new food they have never seen before, or they've never smelled before, they don't eat a big piece of that food. They will only take small amounts. And they decide on the basis on the effect of the food on them, whether they have nausea or something like that, they decide whether to eat that food or not. And if the food produces some harmful effect, then they associate the food with the disease and they will not eat that food anymore. Of course, here there's some learning mechanism. The animal has used some past experience to gain expertise in identifying the safety of that particular food. And if because of past experience, that food has been labeled as a bad food, the animal will predict also that it will have a negative effect in the future. So he is learning, okay? So one could think about extending this approach to the email spam filtering problem. And one naive solution one could think of is, okay, I'm learning by heart. So I look the machine can memorize all the previous emails that have been labeled as spam by the human user. And when a new email arrives, the machine will search whether that machine has already been received and that has been labeled as a spam. If it is not, then it will just go to the inbox. Well, of course, this is not working well, because what is lacking in this way is the ability to generalize. So the ability to get a new email that has never been received before and learn and be able to generalize from the seen examples in order to say, no, this email is spam as well. Okay, and this ability is referred in the literature as inductive reasoning. And rats actually, if they encounter a food that they think it's a negative one, they will not eat not only that specific food, but any other food that smells or looks like that one. So they're able to generalize. And this is exactly what we would like to have with our learning machine. So we would like to get something that is able to generalize. And so if we try to generalize in the spam filtering, then the idea could be, instead of just memorizing all the emails I've seen that have been labeled as spam, well, then what I can do is I can extract a set of recurring words from the emails that have been classified as a spam, and that can be categorized as suspect words. And then when a new emails arrive, the machine can check if any of the suspicious words appear in it and then predict the label accordingly. So in this case, I'm generalizing because I'm using the information, the emails I had, not in a naive way, but I'm trying to learn from my training set. Well, there are some dangers inside the inductive reasoning. And there was an experiment made by the psychologist Skinner. He placed in a group of hungry pigeons in cage. And then there was an automatic mechanism attached to the cage, and there was a window that was opening every, I don't know, like 30 minutes. And every time the window was opening, there was food, okay? So the hungry pigeons went around the cage, and when the food was delivered, each pigeon was doing some activity. For example, one pigeon, let's say, was moving his wings. And so the arrival of food, the pigeon was associating the arrival of food to that movement and kept doing that movement over and over again, thinking that that would help in getting the food, which of course was not true because the food was on a timer, so it didn't depend on their activity. But on the other hand, since they kept doing the activity more and more, they were more and more convinced that that was what was giving them the food. So the result was a chain of events that reinforced the pigeons' association of the food delivery with the action they were performing. So they kept doing it. And of course, this is not something you want to learn. So this is what goes as superstition. It's something that, so a fundamental question is what distinguishes the learning mechanism that leads to superstition from those that are useful to learning. And this is something I want to know because I would like to teach my machine to learn only what is useful and not superstition, right? So, and getting back to rats against pigeons, actually, they tried to make the rats acquire some conditioning between food and electric shock. So whenever the rat was eating, they got some unpleasant stimulus, electrical stimulus. But the rats didn't associate the stimulus to the food, even if that happened many times. And so they knew somehow that the food could not give that kind of consequence, whereas it could give some sickness, but not electric shock. So the rats seem to have some prior preemptive knowledge that tells them that that kind of consequence cannot depend on the food. And this is what is called inductive bias. So inductive bias is some a priori knowledge that has to take into account and influence the learning mechanism. So pigeons are willing to adopt any explanation for food, whereas the rats know that food cannot cause electric shock. So the rat's learning process is following some assumptions that they know they are true. And exploiting prior knowledge about the problem that might influence our learning process is fundamental for getting a successful learning algorithm. And the stronger the prior knowledge, that means I'm doing stronger assumptions in the learning process, the easier it is to learn. On the other hand, of course, the stronger the assumption I'm making, the less flexible is the learning because it is constrained by the assumptions I'm making, okay? And so now that I've given this, rough introduction, we want to give a more rigorous model. So when I'm doing machine learning, I'm assuming I have supervised machine learning. I have an input for my learning algorithm. And this is given by some input space, that is the space of the instances, which is a set X that represents the data I would like to label. So just to give you an example, this is an example that is in the book Introduction to Machine Learning. Assume you're getting to a new island. You have never seen papayas before. You never tried papayas before. And so you want to understand whether it's something you like or not. And so the points in our input space for us are the papayas. And usually the points in our input space are represented by a vector of features. In case of the papaya, you can think of color and softness. And these are random variables, okay? So, and then you have a set of labels, which means the possible values of the labels. For the papayas, this could be bad or tasty, for example. And then you have a training set. What is a training set? A training set is a finite set of pairs in the input-output space and with relative labels. So for example, in our example, is some papayas we have tasted and we have decided whether they were tasty or not. So for each papaya we have tasted, which is our training set, you will have the color, the softness, and the label. And of course, you need to have some representation of both classes. So you need to have some good ones and some bad ones to learn something, or you will only learn the only class you have seen. And what is what you want in output from your supervised learning algorithm? Well, you want a machine learning, which is a function basically that takes an element of the input space and gives you a label. And the label you get predicted, we would like to be as close as possible to the real one, okay? So we would like to have something that given a papaya, I look at the papaya and I say, okay, what's the color? What's the softness? Will I like it or not? And if I think I won't like it, I won't taste that papaya. So I want something that is able to generalize what you have learned from our training set. So given an input vector, our goal is to get a good prediction of the true output, okay? And more formally, we are restricting our attention to some class of function f, and that depends on the inductive bias we are using, so on the assumption we are making on the model. And then we have this vector of parameter alpha that represents a specific function in the class. And that is the thing we have to define when we are learning. So when we are training our machine, we have to assign the values to alpha. And I think most of you are familiar with linear regression. So in linear regression, your class of functions are linear functions. And the parameters you have to learn alpha are the coefficients of your linear regression, for example, okay? And once I've trained my machine is deterministic. So if I give to my machine the same input, I will always get the same output. And in general, it depends in a nonlinear way from my parameters alpha. So that allows to represent complex input-output relationships. And also, in order to get somewhere with my machine learning process, I need to do some assumptions on my training set. In particular, I need to assume that the training set has been generated in accordance with some joint probability distribution P. But this probability distribution is unknown. If I knew that, I would know everything. I only know that it exists. So in practice, what I'm assuming is that each pair in my training set has been independently generated and identically distributed according to this unknown probability distribution. And when I want to train my machine, I need to perform my training process to find a vector of parameters that correspond to selecting one specific function. And the goal, what is our goal? Remember, I want to model the process so that I get the right answer, not on the training set, because I know the labels on the training set. I would like to build a model that is able to generalize, okay? So it is able to give the right answer on never seen before instances and not interpolate my training set. So when I need to choose among all the possible functions, when alpha varies, then I have to define some performance measure. And so what I can do is to introduce a suitable loss function. And my loss function depends on the output of my network, of my learning machine, and the true output. And so what I want, this loss basically is a non-negative quantity that measures the distance between the real output and the output that is produced by my machine, okay? If you think about a classification problem, then what you can take is just the absolute value divided by 2 between the output produced by my learning machine and the output, the real one, y. So this is an error measure in classification. Once I have this loss function, what is that I would like to get? So as I was saying, what I would like ideally to minimize is what is called the effective risk, which is the expected value of the error that I would get on any instance. And this could be computed if I knew my distribution probability. Unfortunately, I don't know P, so I cannot compute the expected risk. So, but keep in mind that when I'm training my learning machine, what I would like to minimize is exactly this function, because I would like my method to perform well everywhere, not only on the training set. But this is something I cannot compute, so I cannot minimize. And so what is that I have? Well, the only thing I have are the L observation of our input-output random variables that are given by the training set. So the idea is I would like to find a function that approximates the expected risk given only the available data. And so what can be done easily is to compute what is called the empirical risk. What is the empirical risk? Is the error I make on my training set. So basically I'm summing up what my loss function on all the examples on my training set. And I know how my model, my learning machine will behave on my training set. So in this case, the empirical risk, I don't have the problem I had before because the probability is not involved. It only depends on the data and on f of alpha. And so I can compute it. And once I've chosen alpha, then that is just a number. And that will be my training error for that value of alpha. So the question is this helpful? How does empirical risk related to expected risk? Well, in general, they are not related. They are not the same thing. Actually, what one would like to do is to find the relationship between the solutions of two different optimization problems. The first one is the one I would like to solve, the one where I'm minimizing my expected risk. But this is not computable. And the second one, which is computable, is the minimization of the empirical risk, which is something I can do. So the question that is natural is, does the error on the training data contains information about what happens on unseen data? Well, the answer in general is no. So look at this example. We have two class classification problems, squares and circles, and both these two separation surfaces, the red one and the green one, make exactly the same error on the training set, which is 0. But if you add new data, depending on which surface you're going to choose, you will get different answer. For example, if I put something in here, the red surface will classify it as square, but the green one will classify it as circle. So from the point of view of the empirical risk, these two surfaces are exactly the same. but they are not the same as generalization capability. So that is one of the problems in machine learning, that you have an objective function, a real objective function that you cannot compute. Okay. So look at this other example. What you would like to avoid are two phenomena when you're doing machine learning. The first one is overfitting, and the second one is underfitting. So look at these examples. You have, again, binary classification problem, square and circles. The pink surface is very simple. The blue surface is much more complex. And if you add new data, you will end up having many errors in both cases, but for completely different reasons. The pink surface is too simple. And so what I'm getting is what is called underfitting. So I've chosen a model that is too simple and is not able to generalize the separation between the data. The other one, if you look at the blue surface, on the training set, that is perfect. It has zero error. But as soon as you add new data, it performs worse than the pink one. So what you're getting is overfitting. I'm chosen a too complex model that is basically interpolating my training set, and it's not able to generalize. So this is exactly what we don't want, because the generalization capability of a trained machine is exactly our final aim. So when we build a machine learning model, we want a model that is able to generalize on new data. And how can we get that? Well, it can be shown that the error that you make on some test instances. So here I'm looking at some data that I did not use on my training set. Well, the error you're going to make will depend on three parts: on the variance of your predictor, the bias of your predictor, and on something you can do anything about it, which is the variance of the irreducible error. So what is this irreducible error? Well, that is the error that depends on the choice of the model you made, or because you did some incorrect assumptions, or because you are not considering some relevant variables, probably because you don't have them. So this is something you can do anything about it. So it's something that you cannot fix. But the other two terms, the variance and the bias of the predictor, those are something you can control. And what you would like to get from this, since this is an error, is to have low variance and low bias. And what is the variance and what is the bias of a predictor? Well, variance of the predictor is how much your predictor would change if you modify slightly your training set. Intuitively, you would like to get something that if you move your training set just a bit, stays quite stable. And that means having low variance. You have high variance if the second you move a bit your training set, then your classifier will move dramatically. On the other hand, by bias, we mean the error that we make by approximating some complex problem by a simpler model. For example, if I'm choosing a linear model, I have high bias because I'm making a strong assumption. I'm saying I'm simplifying my model a lot, then my bias increases. So what I would like to get is something which has low bias and low variance. So look at this picture. On the x-axis, you have the model complexity. And if the model is more complex, my bias is increasing. Sorry, my variance is increasing, my bias is decreasing. And if my model is too complex and on this side of the graphic, then I'm doing overfitting because I'm taking an overly complex model. And so my total error is increasing. If I'm on this side here, I have a simple model, which means that I have high bias, low variance, but my error is still high because I'm doing underfitting. So what I would like to do is to find the right trade-off. So what I need to find is to find my optimum, or at least a very good model complexity that is good for that problem, okay? So the idea is I would like to have a predictor that has low bias and low variance, and then I will keep the total error low, okay? And the error I'm drawing here is not the error on the training set, but it's the error on unseen examples, so the test error, okay? Okay, one could wonder, why do I need to define different classes of predictor? Can I find an optimal predictor for any data distribution? Well, the answer is no. There is what is called the no free lunch theorem that is proven formally, and that tells you that for any predictor, you can find a data distribution where that predictor will perform very poorly. So the idea that you cannot find a model that performs well on any problem. You always will have to try different models and find the right one for your problem, okay? And this is especially true in supervised learning. You will have to do cross-validation. And so you will have to train different models and choose the one that performs best on some set of unseen data. Okay, so unfortunately, machine learning is a lot of try and see what happens. Okay. And in many cases, you have to evaluate the trade-off between speed, accuracy, and complexity of your model. Okay, so now we finally end up with the method. Okay, and I'm going to focus only on supervised classification. So my training set will be a set of patterns where you have D characteristics, so D columns and rows. And then the label, depending if it is a binary classification, it will be just -1 or 1, or if you have more than 2 classes, then your label will be the class the pattern belongs to. And in describing the methods, I will stick with the binary classification because it makes life simpler, but everything can be generalized to multi-class classification. Okay, so the simplest tool we can use are linear classifiers. So look at this example. These 2 sets of points, red circles and blue circles, are what is called linearly separable. So I can find an hyperplane, this black line here, and then I say, okay, I'm going to choose the class 1 if the sign of this quantity, if I'm on this side of the hyperplane, so the sign is positive, I give class 1. If I'm on this side of the hyperplane and the sign is negative, I give class -1. Okay, so the simplest choice you can make. Okay, if my 2 sets are nicely linearly separable, actually, I can find many infinite hyperplanes that separate them. So which one should I choose? And again, look at these examples. I have these 2 sets, squares and circles, and this hyperplane, the dotted one, and this hyperplane, the dotted one, they both make 0 error on the training set because they separate perfectly the 2 sets. But what happens from the generalization capability point of view? Which one is better? So if I add new data, which one will perform better? Well, the intuition is that the one on the right will perform better, because if I add some points here, squares, the hyperplane here will get confused, whereas this one is far away from all the points from the training set, and the intuition is that this will have better generalization capability. And actually, this is true. So the intuition is that a hyperplane that is too close to the training example will be sensitive to noise, and so it won't generalize well. While it sounds reasonable to expect that if your hyperplane is far away from any point of the training set, that will be able to better generalize. So the idea is, okay, I want to keep that into account, and I want to keep into account what is called the margin. So I want to keep into account the distance of the hyperplane from the points of the training set. And so what can be done, I can choose my learning machine in a different way. And I can use what is used in SVM, super vector machine. So my learning machine changes completely. So look at this picture. So I'm going to classify as positive anything that is on this side of the hyperplane, but is also a distance at least rho from my hyperplane. Whereas I'm going to classify as class -1 anything that is on this side of the hyperplane, but with distance again, at least rho. And this rho is what is called margin. And you can prove, there's a beautiful theory, which is called the Vapnin-Chervonensky theory, that among all the hyperplanes that separate your 2 sets of data, the optimal one with respect to generalization capability will be the one with maximum margin. And this is what linear SVM will give you. So they will give you among the linear separation surface the best one in terms of generalization capability. What if the two sets are not linearly separable? We'll get there. We'll get there. And if I have to train a supervector machine, then what I have to do is to solve a convex quadratic optimization problem. So that is an easy, quite an easy task, okay, even for large scale. Okay, there's another approach based on linear classification surface that is simple, but quite effective in many cases, and it's easy to interpret it, which is important. So that is logistic regression. In this case, before I was getting directly the class like class +1 or -1. Now what I'm getting in output is the probability of class membership, not the class membership. And it is a linear classifier as well. So what it does, it assigns a weight to each feature, so to each column of my data set, plus I have an intercept. And then what I do, it models the probability of class membership using the logistic function that has this shape in the picture. And so you can see that I can define my probability of being class 1 and probability of being class 0 in these two different ways. And if we look for a second at this expression, of course, you can see that they sum up to 1, so they are non-negative. They sum up to 1, they are probabilities. And if you look at this expression, you can see that if this quantity here, which is a linear hyperplane, is positive and big, then this number goes to 0 and my probability goes to 1. Whereas if this quantity is negative and big, then the probability that goes to 1 is the probability of having class 0. So again, what I'm exploiting is you see the hyperplane here. What we had before as W now is theta. What was before B now is theta 0, but the idea is the same. And I only have to choose now this coefficient, and I can do that by maximizing some log likelihood function. And also this is an easy task. So this is something that can be done easily. And looking at the idea, well, this quantity here that drives my probability, well, that is proportional to the distance from the hyperplane. So what happens here that if I'm on this side of the hyperplane and far away from my hyperplane, then my probability of being positive goes to 1. If I'm on this side of the hyperplane, then my probability of being negative class goes to 1. And if I'm close to the hyperplane, well, basically, I'm not sure anymore. So what happens is that if I'm exactly on the hyperplane, my two probabilities are 1/2 and 1/2. So that basically means I don't know exactly what class I'm in, okay? So in this case, we're using more or less the same concept we were using in SVM, but now we are producing a probability. And again, the probability is proportional to the distance from my hyperplane. So the idea is more or less the same. So what happens though? Now I'm assuming that the hyperplane exists, but sometimes that is not true. So the question is, what happens? What can I do if the linear separation is not enough? Well, in that case, the idea is, okay, what if I go from my original space to what is called the feature space of larger size? And then I hope that since I'm going to a larger space, I'm adding new features, then in the new space, my two sets become linearly separable. So what is the idea? Think about the data set where I have two features, weight and height for each person. And I have to, my label is decided on the basis whether that person is overweight or not. Well, if I look at the feature that I get by simply combining in a nonlinear way, weight and height, which is weight divided height square, well, I'm not adding completely new information. I'm transforming the information I had. I'm adding a new feature. Well, the problem becomes simpler because that feature is very informative. And so the idea is that if I am in my original space, like in this picture, my two sets are not linearly separable, they can become linearly separable if I add the third dimension. And so in this case, you see, I can find in the feature space, which is the largest one, a linear decision surface that separates them. And so careful, so in the feature space, the two sets become linearly separable. But when I get back to my input space, what was linear now is nonlinear. So you see here in the three-dimensional space, my separation surface is a hyperplane. But when I get back to my input space, my separation surface has become nonlinear. And this can be done very efficiently with what is called the kernel trick, which I have no time to describe you, but that can be used both in SVM, producing nonlinear SVM, and in logistic regression. So you can use kernel also in logistic regression. So they can be generalized in order to produce some nonlinear separation surface in our input space, okay? Actually, you can also go to infinite dimensional space, okay, where everything is separable. Okay, another important tool for doing classification are decision trees. What are decision trees? Well, in decision tree, the classification process is modeled through a set of hierarchical decisions arranged in a tree structure. And at the beginning, I have one single node where I have my entire training set. And then I have to take a split decision at each node. And of course, I only do a split if I have points belonging to different classes in my current node. So, and I have two types of nodes, the internal ones where I have to split and get children, and the leaf node. The leaf node is something node I don't want to split anymore. And I label the node with the majority class of the points in that leaf. And if I have a node where all points belong to the same class, well, that is a leaf for sure. And the simplest stopping criterion is that I only have leaf nodes where I have points all belonging to the same class. So just to give you, describing decision trees is much simpler with an example. So in this case, you have this data set. So you have some charitable organization that gets donations. And for each potential donor, they record age and salary and whether the person was a donor or not. And as you can see here, so what I would like to do is to find a criterion that divides the rows of the data set so that I get, so at the beginning, my root node is the entire data set. I want to split my data set in such a way that the two children are as homogeneous as possible in terms of class membership. And well, the criterion might involve only one attribute or more than one attribute. And so look at these two examples here. So the first possibility is say, okay, I'm looking at my data set again, and you see that the people are ordered by age. And up to below 50, no one is donating apart from one. And above 50, everybody is donating apart from one. So a very good split criterion is dividing with respect to the age. So then given the age below 50, the only one that is donating here has the high salary. So you see if the salary is greater than 60,000, then I only get one person and this is a donor. And as you see here, these are leaf nodes because I only have people of the same class in the node. Same thing on the other side. If the age is greater than 50, the only one that is not donating is the one that has a low salary here. You see here, 25,000. And so again, I can split, and in the end, I only have leaf nodes here. So this is an example of decision tree. And the question is, how do I use this decision tree? Well, if I get a new person and I have to decide, will he be donating or not? Then I look at the root and I say, okay, how old is he? Is he older than 50? Okay, then I go on this side. How is his salary? Lower than 50,000? Okay, then he's not going to donate. So as you can see, this is extremely interpretable. Okay, and so this is what makes this instrument extremely powerful because it's something that you can easily explain to people and can be easily implemented. Okay, so you could do even better if you look at two attributes at the time. You get a tree that is less depth. So, but I don't want to. I'm running out of time, so I don't want to spend too much time on decision tree. But once the split criterion you can get at each node, that depends on the kind of attribute you have. And that, of course, if you have a binary attribute, you only have one possible split. If you have non-binary, then you have different splits. And if you have a continuous, the typical split is the ones we have seen before. But then how do you choose what attribute you want to split on? That's a good question. Well, as we have seen in the example, we would like to get nodes in the children that have homogeneous class distribution. So this node on the left is a disaster because both classes have equal probability. So this is something we don't want. On the right, there's something we do want because we have an homogeneous node and we have one dominant class, okay? So how do you choose? Well, there are different criteria that you can decide to minimize or maximize depending on the criterion. But the idea is that all these criteria will give you children that are as homogeneous as possible. So when you have to build a decision tree, basically you use some greedy algorithm where you, at the beginning, you only have the root node, then you choose which node to split. And on the basis of your criterion that you've chosen at the beginning, you will choose with respect to what attribute you want to split, okay? And you could stop in principle when you get 100% of accuracy in your training set. So you can get leaf nodes where you only have points of belonging to one class. The only problem is that that might require a large number of levels. So the tree could be very deep. And the advantages is that they are extremely interpretable. The training is computationally cheap. They are fast in classifying new items, and the accuracy is quite good most of the time. But the problem is that they usually have overfitting. So they are sensitive to noise and outliers. And this is because the way you are building the tree, you are considering you want to get 100% basically. But you can reduce this effect by doing some pruning of the tree. So you can remove some subtrees of your tree in order to get a better generalization ability, or you can combine different trees in a random forest. And in that case, again, you are building, you are combining the output of different decision trees. And in that way, you are less sensitive to noise and you are reducing the overfitting, okay? And I don't think I will have time to do all I thought, but what I would like to tell you is another classifier that is extremely simple, surprisingly simple, and that in some context is extremely hard to beat. So it's very competitive. And this is the idea is very simple. I take the point I want to classify. I decide that a size of my neighborhood, let's say 15, okay? I looked at the 15 closest points in my training set, and close means with respect to a suitable distance. If you have continuous features, think about the Euclidean distance, okay? And then I say, okay, I assign the class that has the highest frequency in the neighborhood. So it's some kind of majority vote, okay? And of course, the way you choose K changes dramatically the effect. So you can control K. And when K is equal to 1, you get a decision boundary that is extremely flexible, but that leads you to a very high variance. So you're not doing any assumptions, so your bias is very low of this classifier, but the variance is extremely high. When K grows, the method becomes less flexible and the decision boundary becomes a bit close to the linear one. And in this case, you get low variance, but high bias because you are increasing K. Just to show, and the interesting thing here is that differently from all the other methods, you're not assuming a specific form of your predictor, but so it is what is called the non-parametric method. So look at this example here. You have two classes, yellow and blue. And if you take K and N with K equals 15, look at the boundary you get. Well, that performs quite well. Look what happens if K is equal to 1. If K is equal to 1, you get 0 error on the training set, but you understand that this, I have low bias, but the variance is too high. This predictor is extremely unstable. If I add new data, so here I'm really interpolating the training set, whereas this separation surface is pretty good. It's much better than what you would get with the linear separation surface, okay? And the problem with K and N is that it suffers the curse of dimensionality in the sense that if the number of features is high, then the K observations that are near may not be near anymore because the distance might explode. So then the prediction might become poor. So if you have a very high number of columns, you don't want to use K and N. But if you have a number of columns that is small with respect to the number of examples you have, this is something that is worth to try. And for example, if you're doing time series classification in some context, this might be really the competitor you should try to be. Okay. In general, if you look at different techniques, then you can look at the impact on variance and bias trade-off. Remember, the test error depends on bias and variance of your predictor. And so depending on the technique you choose, you are moving one or the other in one or another direction. And I think this table is extremely nice and extremely useful in this sense. I don't have time to go into the details, but it's something, if you want to look at it in depth, this will tell you what are the effects of making some choices. As an example, just to give you an example, if I do a shallow decision tree, meaning that I don't want a very deep decision trees, sorry, then I have a high bias because I'm doing a big assumption. I'm saying, come on, I'm only want depth 4. Okay, so my bias is high, but my classifier will be stable. So my variance will be low because the top split of my decision tree will not depend on minor data variation. So my variance will be low. On the other hand, if I allow the tree to become deep, then of course my bias becomes low, but my variance becomes much higher because then I am very sensitive to outliers. So you really have to make choices depending on your specific problem. And the more knowledge you can combine, the better will be your results. So I'm out of time, so I'm not going to talk to you about this ensemble, but I would like to tell you just one thing. So one very good possibility is to combine the output of multiple classifiers or to perturb your data set and train the same classifier on different perturbation of your data set and then combine the output. Because in this way, which is what ensemble methods do, in this way you're able to take the good part of each classifier or to remove all the effects of the moving of the data set. So in some sense, you are keeping low both bias and variance. So basically, I would stop here. The last thing I want to tell you is what happens if we have regression problems. I only spoke about classification. Well, theoretically, the best option are neural networks, and Bernard in our talk will talk about it. And actually, I didn't have time to go through them, but neural networks can be used for classification too. So it's something I unfortunately did not cover. And that's basically what I wanted to tell you.
Thank you, Veronica, for this very nice presentation and very pedagogic one. So now is the time for the question. So please, can you ask your question in the Q&A in
I
the
don't
Zoom?
find anymore. Okay.
Yeah. Donc du coup, n'hésitez pas à écrire vos questions. Je les relirai en direct. Du coup, vous avez, voilà, j'ai le pouvoir de parler à votre place. Donc, j'essaierai de transcrire correctement vos questions. Donc, en attendant que les questions arrivent, donc j'espère qu'elles seront nombreuses, j'en ai quelques-unes. So, Veronica, I propose in order to wait some questions, I will ask some questions for you. In particular, I'm interested about the last part of your talk because you said in the slide 51, I think, you like to combine the different methodology.
No, ensemble then. This one.
Yeah, this one, sorry.
Okay.
Yeah,
Sure.
and of course, I'm interested how to combine because...
Okay, that depends. So you have two possibilities actually, because you have two main streams of ensemble. So the first one is where you are the data-centered ensemble, where you choose one single classifier, for example, decision tree. So you take decision tree, but you train many of them, not just one. And each one of these is trained on a perturbation of your training set. So you're introducing, like, for example, you take random subsets of your training set. Or, for example, you don't take all the features, you take just a small subset. And so that's what is done in random forest. So that is an ensemble. And then in the end, if you're doing classification, then you do a majority vote, basically. So you do a majority vote, and then you have many decision trees, and then you will give the label that is given by the majority of the decision trees you have, for example. If you're doing regression, then you may have an average of the predictions or something like that. So that is one possibility. The other one is, I'm not going to use one single classifier. I'm using different models. For example, I'm taking one decision tree, one SVM, logistic regression, and whatever you want. And then I'm using, but this time I'm using the same training set for all of them. So I'm training all the different classifiers on the same training set. And then again, when I have to decide what is my label, if I'm doing classification, I do a majority vote. If I do a regression, I take the average. In some cases, you don't take exactly the average or the majority. In some cases, you can decide to weight some classifiers more than others. So that is something then you can decide. You could actually decide to give different weights to the different tools depending on how much you trust them. And then you get the output accordingly. In general, this increases accuracy most of the time. So if your aim is accuracy, this helps a lot. The reason why it's not fantastic is that you lose in interpretability. So if you think about a single classifier, then you can try to get some insights on the problem. If you have more than one, then that becomes difficult. Think about decision trees against random forest. With decision tree, if you're explaining, like I always make the example of medical decision. If you're doing decision support to some doctor and you have to explain that you have to take some choices because your neural network said so, he will never believe you. If you give him a decision tree, which is a chain of if, saying, okay, if this blood value is higher than this, and this other measurement is lower than that, and then this other thing happened, that is something that he will understand. So interpretability in some contexts is extremely important. So when you do ensemble, you lose something in interpretability.
Okay, thank you very much. Some question. If you have a bimodal or trimodal distribution, how do you choose the kernel?
Say that again.
Okay, if you have a bimodal or trimodal distribution, how do you choose the kernel?
Well, choosing the kernel is, again, cross-validation. You try different kernels and then you see what happens. So you don't, in machine learning, almost everything is like that. So you try different kernels, you will have some validation set, and then you will see the one that performs better. So in general, in some cases, there's some literature on how to define the optimal kernel for your problem, but that is something, you know.
And the question is, can you explain? Oh, I cannot understand well. Can you explain the transition between the kernel rest neighbor and the classification?
Yes. So when you're doing classification with KNN, you say, okay, I look at one point, at each point of my training set. Let's say that I've chosen K equal to 2, 3. So I'm taking the 2 or 3 closest points to my point X I'm looking at. And then I say, okay, let's say that these are point 1, 5, and 7. And I look at the class label for each one of these, and then I take a majority vote of that. So that's how it works. That's basically a majority vote. If I'm doing regression, I'm taking the average of the output of my neighborhood.
Okay, thank you. And another question. Okay, just so some participants would like to have your feedback or on the applying machine learning technique on the industrial process data, especially on high frequency time series and or IoT sensor data. Are some methods are more relevant or to be avoided? So we would like to have some, is in discussion.
Okay. Let's say that actually I've been working on time series. So I can tell you that machine learning can work so let's say depends on what you have to do. If you have to do pure forecast and you have a structured time series, then you can use standard statistical methods, and that is going to work quite well. So if you have some trends, some seasonality, and then that can work nicely. But if you have some very unstable time series and you have some external factors you have to take into account, then you want to use machine learning techniques. As an example, neural networks can work really well in that case. So you have some different neural networks that you can apply to that kind of time series. So it can help a lot in that context. Yeah.
Okay.
Okay, that depends a lot on the context. I read the question. So you're asking me how many data you need to make a decision. Well, that is really context depending. So if you, and also depends on the machine learning tool you're using. If you're using like a deep neural network, you need a huge amount of data or you will never train your network. If you wanted to solve some let's say that if you want to solve some problem where you have a small dimensional data set, then you have to look at decision trees, SVM, stuff like this. So it's not a question, it really depends on the problem. So it's not something that you can dimension in general. So that really depends on the application. In some applications, like for some medical data sets, they have some very small data sets. One could be surprised of how small they can be. Whereas in other contexts, you have these huge data sets and they might not be enough. So that really depends on the application. Just to give you an example, if you want to train a deep neural network because you want to learn something like, for example, like electronic consumption, disaggregation or stuff like that, you need thousands of data. Whereas in other contexts, 100 is more than enough. In medical context, 100 is more than enough. So that really depends on the context.
Okay, and perhaps the last question is made by Roda. Do you consider that the deep learning approach is a magic approach which can solve any kind of problem?
Absolutely not. No, I have to be honest. I've been using deep learning, so I shouldn't say that. But the truth is, I think the deep learning is needed whenever you have some structured data. So having many layers will allow to capture structured data. So as an example, for images, they are fantastic. So if you are dealing with images, deep networks are really what you should use. For some kind of temporal dependencies, you will need deep networks again, because otherwise you cannot capture temporal dependencies. So in that case, again, you need deep networks. In some kind of multivariate time series, you will need deep networks. But if you have a simple regression problem or a simple classification problem, then using deep networks is completely stupid.
Okay, so I would like to stop the question. And thank you very much, Veronica, for this nice presentation. And now I propose of Bernardetta to present the talk about combining global optimization with machine learning for the design membrane. So, Bernardetta, the floor is yours. Bernardetta, your microphone is turned off.
Oh, okay, now it's good?
Yeah.
Okay, let's see. The screen is good?
Yeah, now it's good.
Thank you very much. So first of all, I want to thank you to give us this opportunity to talk to these nice Zoom sessions. And what I would like to show you, it's part of the work of a collaboration that is starting many years ago, let's say some years ago, many it's kind of too much, between LORIA, my laboratory, that is a computer science laboratory, LRGP, that everybody knows here, in particular with Christophe Castel and Eric Favre, and last but not least, Veronica Piccialli from the University of Roma. And I will tell you something that maybe you already know, so just sorry about that, but I need some introduction to introduce my model. So I'll tell you something that you know, but I need it. So we'll talk about membrane separation processes. And membrane separation processes are very well known and very used in several industrial applications. So biogas purification, CO2 capture, hydrogen recovery, and the nitrogen production from air. And what's the idea under membrane separation is that membranes are selective barrier activated by pressure. So what you can have is that you have a mix of gases that enter your membrane, and from the output you have a higher concentration of one gas, one component of your gas, and another part of it just pass through the membrane, and so you have a separation of your mixture in the two components. Let's make it simple and say two components. Of course, reality is a little bit more complicated as usual. So a real membrane doesn't separate perfectly a mixture of gas. So we have our inlet flow, the feed with the composition, and then we have two outputs, but each of them has just a higher concentration of one component, but still something over the other one is still there. So the blue, small blue dot here. And the permitted flow is in kind of the opposite. Of course, for let's say we don't lose material, so we have conservation flows. And so the sum of the flows of retentate and permitted flow will be the feed. So why I'm considering this and why I tell you this? Because the point is why we talk about optimization in this context. Because in fact, from the process synthesis community, the behavior of single membrane is well understood, and there exist tools, simulation softwares, for example, Aspin or ProSim, that combined with the module MEMSIC, allow you to simulate a membrane process. The question is that when you want to obtain a design that is effective, what I mean for effective is that it has contained cost and, for example, higher requirements, so higher purity in the output. You don't need just one membrane, but you need, for example, several stages. So you need to combine several membranes in an overall design. And you have to decide also their operational conditions, for example, the pressure, the size of the membrane, and so on and so forth. So the thing is that you need to explore a large space of possibility to find the best design. And this is the place where optimizations enter in the play. So just doing simulation means a lot of long work and the possibility to lose some interesting solution. So the idea is to do some already small intelligent methods, so some artificial intelligence even in here, and give the machine the ability to search for you the best configuration. So to apply optimization methods, what you need is a model. So you have to model your system, and to do that, you have to ask you some questions. So what is given or fixed for you? What are the parameters of your problem? I just give here an example. For example, we can think that the feed, the input is fixed in quantity and composition. And for example, the permeability of the membrane that I choose is a fixed parameter. Then I ask to myself what I can decide. So how I can define different designs. I can decide the size of each membrane, the pressure up and down for each membrane, and the connection between membranes. For example, how much retentate flow from membrane 1 is going to membrane 2. And last but not least, I have to write down constraints. So rules that allow me to choose just only solution that then I can realize. So I have to impose constraints, mass conservation constraints, equation that represent the physical behavior of each membrane, and bounds on my operational conditions. So I will not show you the overall model. Maybe some people already know, and it will take too much time. But I want to show you just a part of the model because it's the part where we'll intervene with machine learning. So we can represent the model as a multi-level model. So we have the system level, the green one, that is the one feed and the two outputs. Then we have a stage level, that is each membrane, each stage with the connection with the other membranes. These are physical elements that are reported in the mathematical model. And then we have something that is present just in the mathematical model, but doesn't exist in the real system. It's what we call the cell level. So to represent the behavior of the membrane, that is nonlinear behavior, that normally is defined by differential equations, we need to discretize them. So we have to discretize the size of the membrane, the area of the membrane, and to represent a set of discretized differential equations to represent the behavior of a single membrane. The important thing is which shapes this equation have. So here we have our membrane, and on the right side, I have just a schematic view. So each small rectangle here, it's what I call a cell, so a discretization step. And what we have here, it's the entering flow, for example, for the oxygen. I'll take the example of N2O2 separation, just to give some concrete example. You can choose another one, of course. And what is the rule that connects the entering flow of the cell to the two output flows? This rule can be written down here for the oxygen. So the permitted flow of the oxygen is related to a cubic equality constraint to the sides of the cell, the permeability of the membrane with respect to the oxygen, and the two relative pressures of the retentated flow and the permitted flow. The important thing is here you have cubic equalities and you have a lot of them. Because if you want to have a model that is a high quality definition, you need to have a small step of discretization. And so you need many of these equations. And of course, you have the same for each component. Here we have oxygen and nitrogen, for example. Then you have component balance in output flows that are linear constraints. And you have constraints that interconnect cell by cell. So you know that the output of one cell is the input of the next one. This is these equations help you to represent the behavior of the cell. So the quantity of gas that is flowing through the membrane, the one that is going along it. And of course, you need to add equations to connect this part of the model to the equations that relate the single membrane, so the overall membrane. So here for the permeability flow, you have quadratic equations because the permitted flow is the sum of the permitted flows of all the cells. And for the both for oxygen and nitrogen, and for the retentated flow, you have the retentated flow of the last cell is the retentated flow of the overall system. So what is the message here? You have a lot of equations to discretize your problem, and they are cubic, so they are not convex. If we look very far distant to overall the overall model, what we have. At each level, we have flow conservation constraints and component balance. So molar fraction must sum up to 1. So these are, let's say, kind of nice constraints from the optimization point of view. Then we have constraints that connect the different levels. Here we have flow conservation again, and interconnection between single membrane and cells that, as we already saw, are quadratic. And then again, we already saw them into detail. We have a high number of at least cubic equation in cascade. So, of course, we have to add to have a full model performance constraints. For example, you can ask for a given purity for your output and at least one level of recovery. So the overall model that you have, it's a little bit impressive, but don't worry, I will not enter again to this. To sum up with that, we have to write an objective function. So you have to decide when a solution is good for you. Of course, a solution must be feasible, so you can need to be able to realize it physically, but also you want a solution that is effective from the cost point of view. In our application, we use a realistic overall cost to consider both CapEx and OpEx of all the devices in the system. So what's the consequence of this kind of model? Is that if you look from the mathematical point of view, you have a problem that have multiple local minima. So we have just not one local minimum, but you have multiple ones, and you can have many, many of them. So you are in the area of global optimization. And in some cases, you have also discrete variables, because in some cases, some variables can be discrete. For example, if you want to choose with different kind of membranes, let's say you have taken 1, 2, or 3, and you want let your algorithm to choose for you the kind of membrane that is the best one for your problem. And last but not least, a huge number of variables. So the problem, what's the problem here is that you write a nice model, you can represent everything with it, but you cannot solve it. If you take state-of-the-art solvers, even the good ones, even the one that write to you, I can solve global optimization with mixed integer variables, you can expect that you cannot solve your problem. So the idea is design your own method to solve your problem. And this is what we did. I will not show you what we use exactly inside our algorithm because it's a little bit more complicated, but I just give you a core idea of what one point that is very important for me to solve effectively these kind of problems. So let's say that you have a function that is not monotone. So this curve here that is going up and down. And what you can do is using stochastic algorithm, like, for example, maybe you know simulated annealing, that are methods that start from a random point and then look around this point to find if they can find something better. But what we do here, it's something more. So we mix two things, a global vision of the function with the local vision of the function. So when you start from a random point here, the red here, point here, you perform a standard local search. Let's say a gradient descent method or something adapted to your problem. And then you look around your point and you search around your point if you can find something better. For example, here, I can just randomly generate in this blue part here. So let's say I just get this point. I perform a local search from here. And then I say, okay, this is better. So I move from this point. So if you have just one valley, with this method, if you implement it well, you can go down, descend this, let's say, start case that I show you here. That doesn't exist in reality, but is the result of a local optimization. If you have multiple minima, you have to do something a little bit more complicated that I will not enter here into detail, but there are techniques to globalize more your algorithm. And of course, you can be lucky also and start from here and go here, take local search, move, and at the end converge. So the point is you use globalization and standard local search. You can use solver off the shelf to insert in your algorithm to increase the performance of your method, search method. So with these ideas behind, a little bit more complicated, but with these main ideas, so a model and the global optimization algorithm mixing with local search, we have a software that allows us to solve several case studies and propose solutions for some of them. So just mention here the CO2 capture, the work on biogas upgrading, and one on nitrogen production from air. And what is the advantage of using global optimization on some problem like that is that mixing local search with global optimization, you can explore the space continuously. So against the simulation, we can move from one solution to a nearest one without losing them. So we have less holes in our search space using local search. And we can reduce bias because we have kind of, let's say, blind search. We don't put too much knowledge in the algorithm. We let the algorithm to explore the space so we can have the opportunity to find innovative designs. But of course, nothing is free, and we have also some difficulties with this kind of approach. And we have a large search space. And so we need to perform a standard local search a high number of times. Local search can be costly. And why can be costly? Because our model is a large size model. As I told you, due to discretization, the higher precision we want, the higher number of equations we have. And we have convergence problems because a high number of nonlinear equalities. Equality constraints are always very, very bad for optimization. So what we want to do is the method works well, but we want to go further. We want to make it work better. So be faster, be more stable. And so this is the reason why we move to use machine learning. So we want to do something, we want to change our model because we think that our model is too complex to optimize it well. So the idea is we want to inject some machine learning in our optimization model. And where we want to inject it. Here you have this summary of the description of the model. If you remember, I tell this discretization part is the one that is the trickiest because they have the highest number of equations and they are at least cubic equations. So what we want to take this part of the model and put inside a machine learning model. Still equations, but obtained from machine learning. And of course, then we have to take care here in this part of connection to connect the single membrane behavior with the cell that was connected to the cell with the machine learning variables. We need some properties. So we cannot use any machine learning method because we want to inject it in the optimization. So we want a machine learning method that produces equations and produce as equations that are not too complicated because we want to remove the complexity to make it something simpler. If we introduce a deep learning technique here, then we gain anything. So we want a simple model to reduce numerical instability, but we want also good accuracy in a wide windows of the variables values. And this is tricky because in fact, we have some variables that I call, let's say, direct, the pressure, the area, the design variables. And the range is known because we choose the range of these variables. But then we have what I call indirect variables. For example, the flow in quantity and composition for each membrane. As we are considering a multi-stage system, first of all, we don't know what exit from any single stage, because otherwise we already know the solution of our problem. But even more, we can have feedback flows, we can have a splitting of flows that we don't know until we solve the problem. So what we have is that for some variables, the range of variation is not well defined. We can have some guess, but we have not precise bounds. And this makes constructing model more difficult. So what is the solution to these two problems for us? First of all, we focus on neural networks. Veronica told you that I will explain to you neural networks. She was lying. I will just give you the general idea of what we used. So what is how you can think about a neuron? So in mathematics, of course. For me, a neuron, what is? You have several inputs and you want to obtain an output. And so what you do is that you combine with the transfer function these inputs through weights to obtain your output. So in some sense, you have kind of a small regression. And you have to determine the best weight for obtaining from your input the desired output. So you can imagine this as a small predictor, and through your transfer function and the accurate choice of weights, you predict one output. One single neuron is not enough to have a good model. So what you can do is you can combine multiple neurons in a neural network. Here I show you a forward network. Of course, there are other kinds, but we want to stay simple. So forward networks was our choice. So what we have here, you have your inputs, you have your network, and then you have your output. Let's say that from this input, I want to guess my output. So I want to choose weights and the opportune transfer functions that represent at best the relationship between my input and my output. So I'm constructing a predictor. And why neural networks? Because there is this nice theorem of 1989 that shows that even a two-layer multi-layer perceptron with just one hidden layer, so I can remove this part here, just keeping one hidden layer and the linear output. So here put just linear functions and obtain a universal approximator. So any nonlinear function can be represented by a neural network. So this is because we want something simple that have a good capacity of approximating. So we stay on shallow multi-layer perceptron. And the other one is we have this high variability of variables. So how to manage that? We move from an equation-based model that is dimensional to an adimensional version of the model. So thanks to the shape of the equation that represent the membrane, we can do that. So we can compact some of the input variables in some adimensional variables. So instead of having pressure up and down, we can use the pressure ratio as an input, phi here. And another parameter is called the adimensional area. I'll show you the equation later. That represent a new input. So I'm reducing the number of inputs and I'm compacting them in something that is, let's say, that can manage a bit more their variability. And I can do also the same for the output. So I introduce the stage cut that is permitted flow divided by retentate plus permitted flow. So in this way, I just go a little bit away from the specific problem and I have a model that's a little bit more general. So machine learning is always the key, data generation. So we know which model to use, but we need to produce our data. In this case, we are lucky because we have MEMSIC. So maybe everybody knows, but just repeat what is MEMSIC. It's a simulation software that simulates gas separation processing through a membrane module. And we are lucky in this case because as MEMSIC have been developed in the separation process group of LRGP, we not only have access to MEMSIC, the simulation box, but we have access to a core standalone code that works with the dimensional model. So we don't need to inject MEMSIC in Aspen or ProSim. We just use the core module to produce our data set. So let's see here a schematic view of what we have. So we have MEMSIC here, the input variables of our simulation model. So we have the concentration of one element. I continue to keep N2O2 example. We have the stage cut, and we have the pressure ratio as an input. Then we inject some of the properties of the membrane, so the permeability, to be precise. And as an output, we have the adimensional area and the concentration of the oxygen in the permitted flow. Of course, the other variables that they were before in the model, they can always be obtained through equations that are known. So we produce them a posteriori. So these are only the variables that we look for. And so what we do with that, we generate our data with MEMSIC. And then with this data, we trained our network with just one hidden layer. And what we do is that instead of having here, we have input and output. And here we have the same input of MEMSIC, and we have predicted output. And so what's the good news is that with the one single model, we have a high range of variables with high precision. So we get a model that has an error of 10 to the minus 7, 8 in precision. So it's very, very accurate model. And we have a high variability in the inputs, because you see here with the variability of 0, 1 in these variables, x, theta, and phi, I can obtain all the span of the variables that I want. So this is also a good feature because when you train a neural network, having normalized inputs is always a good strategy to allow the neural network to find the good weights. But then what we did is we have our model, and we inject the equation obtained from the machine learning in our model. So we take the equations and the weights that we obtained, and we put at the place of the cell equations, and we introduce connecting constraints from the machine learning equation and the original optimization equations. I'll show you just very, very few results, not the details, for a case study. It is nitrogen production from air. So the good news is that we have a high reduction in computational time. I just show you the results for 50 multi-star trials. So we just extract 50 random points and perform a local set from them. And I just focus on purity. We ask 99.9 purity, and we look at the two-stage system here. We see that the number of unfeasible solutions that the original problem found was 40 over 50 trials. So let's say that just 5% of the time we found something that is beautiful, and the rest was just trash. And with the machine learning, we have 14 times that we have unfeasible solutions. So the improvement in the number of trials that are effective is very important. But the most impressive thing is the time, the computational time. For the same case study, we need, let's say, a little bit less than 1 hour to run 50 trials with the original model, so the full equation based from physics, and using this integration of physics and machine learning, we go down to 20 seconds. So we have 2 orders of magnitudes of reduction in the computational time. That you can imagine the time that you can allow to search better your search space if you have this. But of course, there is always bad news in my slide. What we observe that if we look at this final solution of the optimization for high purity, the quality of the solution with respect to simulation was not perfect. So what we obtain is that when we go to simulate the 99% of purity, purity was not 99%. So our model alone, the machine learning model alone, is very good, but you put it in the optimization and you find something that is not good enough. So why that? Because you have a model with a 10⁻⁷ precision and then it's not working. What's the problem? Problem is that you connect this model inside an optimization and you have error propagation. Here, I told you here we use this adimensional area to help the machine learning to work in normalized variables, but the original optimization variable is the area, because the cost depends on the real area, not on the adimensional area, of course. And this relationship introduces some errors. In fact, depending on the unit of measure that you use, this coefficient here, it's very big. It's around 10⁵. That does mean that your error that was small is not so small anymore. So you have a small error on a dimensional area, but you have a small but not so small error on the area. So the propagation of the error due to nonlinearity is high. So what you do in this case? What we did is that we reverse one input with one output. So we decided that for the machine learning, the input is the adimensional area. So we have full control of this variable that is very sensitive to errors. And we put out the stage cut that is as a relationship that is less strong, less propagating the error, because we have a ratio of two quantities that are similar in size. So this was the first step to allow us to reduce still the error in machine learning and so improve the performance then when using optimization. Other step is that you can reduce the variable bounds to look in more reasonable region. In fact, the inputs here, you can think, for example, that the concentration is between 0 and 1, because of course it's always true. But if you can reduce a little bit the input in the region that you are really interested in, your performance in the model could be better. And the other one is analyze the error. The problem with all machine learning models that give you average errors. Don't give you the error everywhere. So average, all engineers know that is always a problem. So what you can do is that when you look at the error, don't just look at the value of the error, but look a little bit in depth and see how this error is dispersed on your data. So you can use, of course, classical statistical analysis to look at the error distribution on your data. But also you can use what you already saw from Veronica. And what we decided to use is using decision tree, because we wanted to check if there were some regions that are better modeled and some regions that are worst modeled. Because the problem when you inject a machine learning model in optimization is that optimization will go around in the space, look everywhere. So your model must be good everywhere, not in average, everywhere good. So what we did is that we label our points depending on the error. So 1, if the error is larger than a given threshold that for us was not acceptable, and 0 otherwise. And then we construct our tree using these labels, and these allow you to identify regions of the input variable where the majority of point is labeled 0 or 1. So I just zoom the figure because otherwise it's not possible to see anything. So for example, if I just zoom my tree here, what I can say of this blue dark leaf, this is a class 1. So this is a label where I have a lot of errors. I can tell myself if I look at this, so if phi is smaller or equal than 0.03, I go in the yes branch, and if x1, so the concentration of the input is in this case greater or equal than 0.677, and the dimensional area is greater than 0.9069, then I have a big quantity of points where the error is high. Because you see here you have the number of points where class is 1 and the number of points when class is 0. So we didn't go below the tree as Veronica showed to you to have a yes or no. We still have some 0 point here, but the majority of point is on the class that you ask for. So how you can use it? You can use it to improve your data set. So you can see here, the modeling is not good. Why don't add points in this region to improve your model? So this is what we did. We identify with this technique the regions that where the model was less precise and inject point in this region to retrain our model to improve its quality in the regions that were not good. So I don't know how much time I have spoke, but I will want to stop here anyway, because it's a lot of things. So what's the lesson that we learn from this? The lessons learned are multiple for me. Of course, it's my opinion. It's that the machine learning techniques can produce interesting model even when physical equations exist. Of course, I think there is a large community that using machine learning model when a physical equation doesn't exist, or you cannot write it down easily because they are too complicated. Here in this case, this equation exists. They seem not too complicated, but then if you want to inject them in an optimization method, they are too much. So maybe in these cases, try with another model to see if you can obtain the same quality of model, but with a faster resolution. How you choose the input and your output of your model is very important. Of course, not just in machine learning, in any kind of modeling, defining what is the input and output of your model, of your predictor, is very important. And you see, if this model is inserted in a more complex system, this is even more important because you have error propagation, you have a nonlinear relationship between variables. So you can change a lot the quality of results just changing input with outputs. And of course, everybody knows this. So data generation is a key element. We were lucky in this case because we could generate our data. In some cases, you have data and you cannot generate or add the data. But when you can add data, you can use other methods to improve the quality of your data. For example, here, you use a decision tree to choose the regions where to generate data. So you can mix machine learning methods to improve something. And last but not least, that's the opposite message. Maybe I'm a computer scientist, but I don't think machine learning is a solution for everything if you don't use it well. So don't throw the baby with the bathwater. It's not because there is machine learning that everything must be done with machine learning. Here we combine optimization, equations, and machine learning. We didn't throw all our model. We didn't try to use machine learning to predict a full system of membranes. We use machine learning for the single membrane, but conservation constraints, we put the equations because they are easy constraints. There is no mean to make machine learning to learn something that you already know perfectly. Machine learning is for when you don't know exactly something, or when you know it with the representation is too complex and you search something easier to use or more robust. But when you know that something is, as you know, you can keep it. So for me, I think the real future is combining machine learning with what we already know. We know to do auto optimization. We know some physical equation that exist. Let's mix them up and keep the best of the methods. Like Veronica told at the end, mixing things. So not just comparing different machine learning methods, but mix techniques that we already know to get the best of what you can get. And thank you very much for your attention.
Yeah, thank you very much. Sorry, I don't find my mouse. So thank you very much for this nice presentation, Bernardetta. Please, if you have some question, can you ask your question in English in the Q&A? And I will translate your question. Okay, the first question is which software and programming language did you use to implement the neural network in the classification trees?
We use Python and how it's called the standard tools that you can find on Python, in fact. So we didn't implement the neural network. We use a standard library on Python, and we just set the parameters and train the neural network. And also for the classification tree.
Okay. Peut-être Patrice Kiener, je ne comprends pas très bien votre question.
Oui, yes, Shikilem. Thank you, Patrice. This Scikit-learn is I think it's the most famous kit for doing machine learning, and it's quite effective, in fact. You can choose the kind of network that you want, the kind of activation function, the number of neurons, quite simply. I don't get the link thing anyway. Okay. Thank you very much. I will read carefully this. I think neural networks are not a new idea. In fact, there was a big boom when I was a young PhD student. Everybody was using neural networks. Then people forgot that, and now they are coming back. So.
Okay. Thank you, Bernardetta, to help me. If you have some, okay, perhaps just Liang Liu would like to know what is the minimum size of the database.
That's depends.
Many questions we have on this topic, on this, how many sample you need, etc. So
what we use in our specific case, we use a huge data set because we could generate our data. So our data set is around 1 million points. But we are lucky, we can generate as much data as we want. So we get them, let's say, just wait a little bit, simulation, do the thing. So we can do that. Yes, of course. In fact, can I answer?
Yeah, of course, of course. Can you please, can you read the question? Because
I can read now, so
no problem, you can read it.
In fact, yes, when you do experiments, you have a limited data size, so you cannot afford 1 million points. We were in a special case where we can generate our data. When you have experiments, you choose, you have to adapt on the size that you have, and then you have to accept that maybe your model is less precise. That's you cannot gain in any point. Of course, maybe you can accept that you have a less precise model. We ask a high precision to our model, so this is the reason also we need a high number of points. We have a precision of 10 to the power -8 on the output. It's quite high for this for neural networks. It's
okay. If you have more questions, please can you ask before the end of the webinar? Okay, we have 2 more questions. Thank you. Okay, Arturo, thank you very much for this presentation. Is there any hybridization between physical machine learning model, especially in case of multi-level model membrane, as presented at the beginning? Thank you in advance.
I'm not sure to have understood the question, but I try to answer then. In fact, our model is a mixed one. It's an hybrid one. The equation that I showed at the beginning, so the cubic equation that represent the membrane are substituted with machine learning, but the other physics equations of flow conservation constraints, for example, are kept as their physical constraints. We didn't model everything with machine learning.
And a second one with Grégoire Léonard. What is the impact of the accuracy of the measurement on the result of the machine learning? How to consider the properly in case of measurement with high standard deviation?
That's, I'm not sure to understand this. Of course, if the measure have already an error, what you need to do when you use machine learning is to learn the data and not learn the error on data. This is a huge problem, and I think Veronica will talk about that. This is between the bias and the variance of the thing. You want to learn just the important data and not the noise. So the thing that is done is they are different. In neural networks, you can use regularization terms. So you add a term that penalize having a too complex model. So you have a balance between the being nearby your data and have a model that is too complex. Or you can use the technique that's called the early stopping, and is that you check, you train your model on a data set, but you check it on a test set. And when the error on this test set increase, you stop to learn, because then you are learning also the noise on your data, because you don't fit anymore the test set.
Okay, so thank you very much, because we have no more questions. Thank you very much, Bernardetta and Veronica, for these 2 nice presentations. And before to close this webinar, I would like to present, just to share my screen, to show you, okay, I would like to show you the symposium Escape. So it will take place in Toulouse in next June. And in this symposium, we have a special topic on digitalization and artificial intelligence. So we have developed a big data management, cloud application, cyber, etc. You can read it. So if you would like to present the result, please show the website and you can submit your abstract. And the deadline is before the 1st of September. If you have some question, you can contact me, because I am one of some organizer of this symposium. Yeah. So this one is just to some link. And I'm sorry, I have last question. No, thanks. Okay, perfect. So So thank you again, Bernardetta and Veronica, for this nice presentation. Merci Martine et Roda pour m'avoir accompagné aujourd'hui. Jean-François, merci pour nous supporter le groupe IAP dans cette dynamique des webinaires avec SFGP.
Juste, Ludovic, si on peut rappeler que les prochaines sessions sont le 16 septembre 2021, avec un focus particulier sur les modèles d'apprentissage dans les procédés. Et la dernière session de l'année sera le 2 décembre 2021, avec un focus sur la mise en pratique des méthodes d'apprentissage, avec notamment un atelier démonstration. Et donc, dans les prochains jours, vous recevrez une invitation avec le détail des sessions qui n'étaient pas encore définies. Voilà. Merci à tous.
Merci beaucoup.
Merci aux deux présentateurs.
Merci encore. Un bon après-midi et une Forza Italia.
Oui, Forza Italia. pour ce soir. Merci à tous et à très vite.
Au revoir. Bye bye.
Au revoir.
Bye. Thank you again.